if you've got any questions, post them in the chat and I will check them throughout. And also you've got Lane and Gavin on standby if you do have any questions that you want to ask whilst I'm discussing the material here. So what we are going to look at today is geometric progressions. But just before we get into that, we'll just do a little recap of what we did in the previous lesson and, well, the previous two lessons, really, on arithmetic sequences. So remember, when we've got an arithmetic sequence, we have a common difference. So this is where we just add or subtract the same number each time to get to the next term. Okay, so 3, 5, 7, 9, 11, 4, 2, 0, minus 2, minus 4. Those are all arithmetic sequences. We know that we call the first term of the sequence A and that we call the common difference D. And then we met some formulae. This one on the left is the one that you won't get in the formula book. So you want to find any term in the sequence. That's the formula you use for UN. So if you want to find the 10th term, you do A plus 9 times D. And if you want to find the sum of the first 10 terms of the arithmetic series, okay, so when we talk about series, we talk about the sum of all the terms, then we use either one of those two formulae. Now, those you do get given in the exam. But in this lesson, we're going to look at geometric progressions. And the difference here is with geometric progressions, we have what we call a common ratio. So a geometric sequence is where each successive term is found from the preceding one by multiplying it by a fixed number called the common ratio. So rather than adding the same number each time like we would with a arithmetic sequence, we're going to multiply by the same number with the geometric series. So we have some examples of geometric progressions below. So 2, 4, 8, 16 is obviously a geometric sequence. We have our first term, and yet again we use A for our first term. So A would be 2, and then R is our common ratio, because we multiply each term by 2 to get to the next one. This sequence is always increasing, and it's what we would call a divergent series, okay? But we will talk more about that a little bit later on in this booklet about what it means by diverging. Basically, all you need to know at this stage is it doesn't converge to a particular number. It's just going to keep getting bigger and bigger and bigger. We can also have geometric sequences such as this: a half, a sixth, an 18th, and a 1 over 54. And each time here, we're multiplying by a third. So the common ratio would just be a third. This is what we'd call a converging sequence. It won't ever reach 0, but it will get closer and closer to that 0. So each time you multiply by 3, you're getting closer and closer to 0. Yet again, we will talk more about converging sequences a little bit later on in this booklet. Then we have periodic sequences. So these are ones that just alternate between particular numbers. So in this case, we've got 7 minus 7, 7 minus 7. This is still a geometric sequence because the common ratio is -1. Each time you multiply by -1 to get to the next term. And yet again, we will look more about periodic sequences a little bit later on in this booklet. And then we can also have a geometric sequence like this. We've got 5, minus 10, 20, minus 40, 80. And this is another divergent sequence. And this time our common ratio is -2. Okay, so we can alternate between positives and negatives and it still be a geometric sequence. Now, what we need to know is this formula here. So we need to learn this. Okay, this won't be in the formula, but we need to learn this formula. To find the nth term of a geometric sequence, we do un equals a times r to the power of n minus 1. So a is the first term in the sequence, and r is the common ratio. So if you want to find any term in the sequence, you use that formula. What this means is the first term of the sequence is a, the second term of the sequence is ar, the third term is ar squared, and so on. Now, when you're finding your common ratio, so to find r, if you're given a sequence of terms, what we can tell about a sequence where we've got a geometric sequence is that if we do a term divided by the previous term, that is going to give us the common ratio. So R, if it is a geometric sequence, you can just do the second term divided by the first term, and that will find you your common ratio. But also, we could do the third term divided by the second term. We could do the fourth term divided by the third term. And in general, if you always divide by the term that came before it, you can find the common ratio in that sequence. Now remember, the key word here is it's a common ratio, so it's always going to be the same. And this fact is going to help us with a question that we do later on. So let's dive in and do some examples then. So the first two examples are just kind of general ones, getting used to the sequence. And then examples 3, 4, and 5 are going to help you with the assignment questions that you've got for today. Now, the first question says, find the 10th term of the geometric sequence 3, 6, 12, 24. To do this, I need to know what A and R are. So A is my first term, so A is just simply 3, and R is the common ratio, so this is 6 divided by 3. I'm just doing my second term divided by the first one, which gives me 2. Note that I could have also done 12 divided by 6, it gives me 2. I could have done 24 divided by 12, it also gives me 2. Then I use the formula UN equals A times R to the power of n minus 1. Substitute in your A and substitute in 2 to the power of 10 minus 1. And we just simply, that's just 3 times 2 to the power of 9. And we just get 1,536 as our answer. Remember, BIDMAS here, you need to do your 2 to the power of 9 first before you multiply it by 3. Don't multiply the 3 and the 2 first. It's a common mistake that we have seen come up before, so make sure you don't fall into that trap. I'll just check the chat, just check if there's any questions. If not, I will progress on to the second example. Now this question says, show that the nth term of the geometric sequence 40 minus 20, 10 minus 5 can be written as the following. So here we have A as 40, our first term. Just to see how we're doing in chat, can you tell me what R is going to be? What is going to be my common ratio for this sequence? Okay, yep. Tilly, Kyle saying -2 there. Excellent. Sharon saying -2 as well. Yep, good. And the thing I want to make sure that you were saying is that you were saying, wait, sorry. No, sorry. No, it's not -2. Just have another think about it. Yes, thank you. So yeah, it's not, sorry, not -2, it's -0.5 or -0.5. We're going to use -0.5 and keep it with the fractions here. So just be careful. But it's good thing to kind of. So I'm glad you kind of said -2 because it kind of brings up a really key point here. We need to do our second term divided by the first one. So we get -0.5 there. So remember, if you had 40, if your common ratio was 2, your next term would be, if it was -2, your next term would be -80, then it'd go positive 160, and so on. And you can see, hopefully, if you do 40 times -0.5, then you get -20. When we talk about common ratio, we're always talking about multiplying to get to the next term. So you might think of this as where you divide by -2 to get to the next term, but we always want to refer to R as what we multiply by. So I'm really glad you put -2 in the chat because it brings up a really key point there. Now what we can do is substitute that into our formula to find our nth term. So UN, this is how we find our nth term. So we're going to do 40 multiplied by -0.5, which is our common ratio, to the power of n minus 1. Now it might look at the moment we're a million miles away from what we're actually trying to show here. So we need to do a little bit of manipulation to get there. Now, if I look at the 40, I can see that I haven't got 40 in what I'm actually being asked to show here. But I have got a 5 and I have got something that's 2 to the power of. So what I want to do is I want to think of 40 as, well, what can I've got a 5 in there. So let's rewrite 40 as 5 times something. So to make 40, we do 5 times 8. Yet again, I haven't got an 8 in there. So what I'm going to do instead is I'm going to think of the number 8 as 2 to the power of 3. And then this bit in the bracket here, I'm going to, because it's all to the power of n minus 1, so it means I need to do the top and bottom of this fraction to the power of n minus 1. So I'm just going to rewrite it as the following. So I'm just going to do -1. I'm going to keep the negative on top because I've got -1 in my answer. So I'm keep the -1 on top and then just do it like this. So I'm just going to come up here to the other side to finish this off then. So what I'm going to do is I'm going to put this -1 to the power of n minus 1 at the front. Okay, that's just this bit. So you can see there, I've already got that bit. And I'm just going to put this 5 on top of the fraction. Rather than multiplying by 2 to the power of 3, that's the same as dividing by 2 to the power of -3. Okay, timesing by 2 to the power of 3 is the same as dividing, by 2 to the power of -3. So then we get this. And then it's just a case of at the end, just multiplying these powers together on my denominator. So I multiply the powers, so I add them together. So I multiply the indices, so I add the powers together. So n minus 1 minus 3, it's just going to be 2n minus 4, and then I've got the result that was required. So it's quite a tricky one in terms of manipulation with the indices, but let me know in the chat if you do have any questions about that, anything else you want me to go over in a bit more detail. I'll just give you a second or so to copy that down, and then we'll move on to examples 3, 4, and 5. Right then, now the questions that you're going to do today after this lesson, they're all going to be exam questions in terms of ones we want to show evidence of. There's still questions to do from textbook to give you further practice, but the ones we want to see is the exam questions. And some of these questions are a little bit tricky. However, if you use these examples as templates, then it's going to help you. Obviously, they're not going to be, 2 questions in a maths exam are never going to be completely identical, but at least there might be similar skills that you use. So this example 3 should help you with question 1, example 4 should help with question 2, etc. Now in this question, you're told the second term of a geometric sequence is 4 and that the fourth term is 8. So let's write down some formulae to summarize that information. So we know that un equals ar to the power of n minus 1. So the second term, u2, is going to be 4. What this means is a times r to the power of n minus 1. So in this case, that's 2 minus 1. So that's just going to be 1. So I know that a times r equals 4. Okay, at this moment, I don't know what a is and I don't know what r is. Then I'm told that the fourth term is 8. So I know that a times r cubed equals 8. Just take care here. It should be a power of 3 here, not power of 4. You might be tempted to think it's the fourth term, so I put r to the power of 4. But of course, it's always n minus 1. So that's why we've got the 3 there. So what I've got here is 2 simultaneous equations. Now, you might not have had as much practice solving simultaneous equations like this. You might have seen a couple of questions like this when we did logarithms and exponentials earlier on in the course. But I know then I think some of you struggled solving simultaneous equations that were in this form because you're not adding terms here, you're multiplying. One way you could do it is rearrange it to make A the subject and substitute that in, but by far the easier way, so just like we can add and subtract simultaneous equations, we can just divide them as well. So I'm going to call them equation 1 and equation 2. I'm going to do equation 2 divided by equation 1. So what happens is when I do AR cubed equals 8 divided by AR equals 4, well, AR cubed divided by AR just gives me R squared. And then 8 divided by 4 just gives me 2. Then I just simply square root both sides and I get R as square root 2. Now I know this contradicts when I normally say you've got to have a positive and a negative. However, we are told that the common ratio is positive here. So I'm just going to take the positive solution. Then what I'm going to do is I'm going to sub R into equation 1. So this just simply gives me A times the square root 2, which equals 4. And then if I do 4 divided by the square root 2, I just get 2 root 2. Okay, you can either simplify, rationalize the denominator with thirds, or just simply put in your calculator to check. But I would recommend that you can rationalize the denominator and do it that way. Now we have A and we have R. So now we can actually answer the question, which is to find the value of the 11th term in the sequence in the form k root 2. So we're leaving it in the exact form here. We're not going to just leave it as a decimal. We do need to leave it in the exact form here. So to find U11, the 11th term, I do A, which is 2 root 2, times R, which is root 2, to the power of n minus 1. So 11 minus 1, which is 10, and I get the following. So you might put it in your calculator, and I haven't actually checked on my calculator, check it would actually work if you do this. Sometimes your calculator doesn't always give you exact answers when you do this. So it is beneficial to either break it up in steps when you put it in your calculator, or just make sure that you're confident with dealing with your indices here. Now, root 2 to the power of 10. So another way of describing root 2 is to say, well, that's 2 to the power of a half. So this is 2 to the power of half to the power of 10. So this is 2 to the power of 5, which is just 32. So we're just doing 32 times 2 root 2. So this just simply gives me 64 root 2. And that is my final answer. Okay, that's the 11th term of the sequence. So this example is going to help you with question 1 from the exam questions that you're going to do in the second half of this lesson. Let me know if in chat you've got any questions so far. Okay, so example 4, and now this one's going to help you with question 2 in the assignment that we want to see the evidence of the questions that you've done. So you're given that number 3, x, and x plus 6 form the first 3 terms of a geometric sequence. This geometric sequence goes 3, x, x plus 6. Find the possible values of x and the corresponding 10th term of the sequence. So firstly, can anyone tell me what the I don't want the actual number yet, but can anyone tell me a way I could write the common ratio of this sequence? So I'm just going to leave that question in the chat. So just in terms of x, can you tell me what the common ratio of this sequence is going to be? Okay, excellent. A lot of people saying x over 3 and saying x over 3, not 3 over x. So I know that x over 3 is the common ratio. Is there another way I could describe the common ratio here? So that's one way we could describe it. However, we don't just want it in terms of x. We want to try and actually find what x is so we can solve this. So is there another way I could write the common ratio? Excellent. So well done if you put x plus 6 over x. So I know these two ratios have to be equal to one another, okay, because it's a common ratio, and the key word there is common. Okay, it's going to be the same whether you do the second term divided by the first term or the third term divided by the second term. Okay, remember u2 over u1 will equal u3 over u2. So now what we have is this equation, and we can multiply both sides by x and multiply both sides by 3. And hopefully now we can see that if we rearrange, we're going to get a quadratic here. And then we just simply solve the quadratic. So this one will be nice and easy to factorize. So we get x equals 6 and x equals -3 as my two solutions. Just be careful here. You can have the negative as your solution. Okay, so this sequence can go 3, 6, 12 if x is 6, or if x is -3, it'd be a periodic sequence and go 3, -3, then +3 again if you put in the -3. So whilst we've looked at before when we did arithmetic series, if we were trying to find n, for example, n had to be positive. But here x, it's just a number in our sequence, so it could possibly be positive or negative. I'm not told that it definitely is positive or negative. So we've got two scenarios. If x is 6, then the common ratio is just going to be 6 divided by 3, which is just going to be 2. And then if we want to find the 10th term, we just find u10. So we just do 3 times 2 to the power of 9, because it's always n minus 1. So 10 minus 1 for the 9. So just always think of it's going to be 1 less than what n is, that power. And when we do that, we get 1,536. So if x is 6, then we get 1,536 as our answer. If x is 3, then the common ratio is going to be, sorry, x is -3, then the common ratio is going to be -3 divided by 3. So the second term divided by the first one. I could also do the third term divided by the second one, still get the same answer of -1. So u10 would just be 3 times -1 to the power of 9. Okay, n is 10, so 10 minus 1 is 9. And I just get -3 when I do that. And that makes sense. If you look at what the sequence is doing, it's going 3, -3, 3, -3. Basically, every odd term is positive, every even term is negative. So you would expect the negative 3 there. You could essentially come to that conclusion without even putting in the formula for u10, because you can see that sequence is periodic. Any questions in the chat? If not, we will move on to the last example of today. So this example will help you with question 3. And it's what is the first term in the geometric progression 3, 6, 12, 24 to exceed 1 million? It might seem that this is going to be a really big number, but you'd actually be surprised how it's not that big of a number at all, because this just is exponentially getting bigger and bigger, very quick rates. So actually, we can get to 1 million very quickly here. Now, this will help you, say, with question 3, and there might be a temptation to just do this trial and error, but you really want to use the logarithms in the exam. If you do trial and error, you've got to make sure you show a lot of different trials and ones either side, and there's also room to make mistakes. And you're going to get, to get that credit, the best way is just doing it with the logarithms, as we're about to see. So we've got a first term of 3, and we've got a common ratio of 6 divided by 3, which is just going to be 2. So we want to set this up in terms of we're looking for that first term that takes us to 1 million. So we're going to do 3 times 2 to the power of n minus 1, where a is our first term of 3, r is our common ratio of 2, and then we've got that power n minus 1. And we're looking to see where this equals 1 million. Make sure you put the right number of zeros. We divide through by 3, as so. And now we want to find this power. Now, remember, if we're trying to find a missing power, we want to use logarithms. Yeah, again, it might be a temptation to do some trial and error here, but we really want to use the technical way of doing it. We want to be very precise with this rather than just kind of doing trial and error. We want to be a bit more accurate than that. So we are going to use logarithms here, and we can just simply switch this into log form by writing log to base 2 of 1 million over 3 equals n minus 1. Remember, when we switch that back to exponential form, we do our base to the power of n minus 1, which gives us the answer of 1 million over 3. So remember how to switch from log form to exponential form and vice versa. Now we can just put this in on our calculator. So on your calculator, you can just do log to base 2 of 1 million over 3, and we get, actually I'll just write down what n is. So we get that, and then we're going to add 1 on so we can find n. So we get 19.347. Now that would give you exactly 1 million, but we can't. We're just talking about number of terms in the sequence, so we know n has to be an integer here. So we're just going to simply round this up to 20. You can, and I believe it in your written notes that you've got for this in the assignment, we used inequalities there, so you can do it with inequalities as well to make sure that you know that you have to actually round it up. But I'm fine with just think of this as, well, 19.347 would take you to exactly 1 million. So you know the 19th term would be slightly below it. The 20th term would be slightly above it. So the 20th term is the first term to exceed 1 million. Now, just a little note before we go on what you've got to do next. So you've still got questions from the textbook to do, so exercise 3C. So still do those questions. Don't just think all we want to see is what you're handing in, just those 5 questions. Make sure you're doing a wide range, just like you would in the class normally. But the ones that we're going to be particularly interested in seeing is those exam questions that are attached. Let us know if you're having any technical difficulties downloading the questions. If you've got any problems with the questions, hopefully you can come back to these examples if you're watching the video later on, then just kind of go back through those examples for the particular exam questions. Remember, there's also homework on there from what we've done previously, so make sure that you look at the homework task for this week, or if there's any homeworks from the past that you haven't yet done, make sure that you do that. Ask us plenty of questions. I'll stick on here if anyone does have any questions. If you would like some more